Okay, we'll go right to the third talk of the day. It's by Professor Arindama Singh of IIT Madras, which is, as you know, a neighboring institute. This talk is on logic, and logic is one of his many research interests. He's interested in workshops for school. He's an expert on, in addition to his being an expert on the research areas, he's also interested in school education, and he's in particular interested in running workshops for school teachers and for school children. So please welcome Professor Arindama Singh.
So can you listen me? No problem? So throughout this lecture, I will be asking you to imagine many things, which may be true, which may be false. Okay, agreed? Sometimes I will ask you to, or I will prompt you to answer some questions. So even if it is not audible, you speak. But after speaking, be silent immediately. Don't linger it. Okay? Then I will be carrying it over. Okay, so let's start with one question. Do you have any tabs with you? Tabs, iPad or Samsung tabs, something? No? Some of you must be using? Yeah? See, at the end of the day, there will be a quiz, you remember? So you have to write the questions. Now I declare, if you answer all the quizzes correctly, I will give you one tab. I am asking you to imagine again. Okay. Is that fine? So assume that this is what I have told you, that if you answer all the questions in the quiz after the end of the day, then I will give you one tab. Whoever does it gets a tab. Right? Should I write it? Okay, fine. So imagine it. It's nice to imagine, so don't worry. Now suppose at the end of the day, one of you has solved all the questions correctly, but I don't give him the tab. Then what you will do? That person will be very dissatisfied, right? So will he say I am wrong or I am right? Will he say I am wrong or I am right? I will be wrong. So I am making a false statement now, right? Yes? Yes or no? So suppose one person has completely solved all the problems correctly, and I give him a tab, right? Then you will be very happy. Okay, he has kept his promise. Yes or no? But imagine a nice situation that you have not solved all the problems correctly, still the organizers have so much money, they allow me to give you each a tab. Okay? So what do you say? Now I am wrong or I am right? Yes, that is correct. That is the meaning of if-then sentence as we use in mathematics. Still you will say that I am correct, I have not violated my condition. Okay? So what does that mean? Suppose you write it in abstract form, if P then Q. Now can you tell me when I am wrong, when I am right? Just write it, if P then Q. Then tell me when I am right, when I am wrong. So, whenever I give you a tablet, I am right. Huh? Yes? Huh. Huh. So, not only that, there is another thing he is telling. Huh? So, now decide, there are 4 cases, correct? Correct? Huh? But you have told something else. If P is false, then I am always right. I am wrong. How? But I give you the tab. So you are happy to receive it, no? So is it right or wrong? Huh? Did I say that if you do not answer them correctly, I will not give you a tab? Did I say that? It might be just a motivator to you to solve all the problems, right? So you have not answered all the questions, but I have given you the tab. Have I contradicted myself? Huh? Now you have to decide. Huh? I have not contradicted myself, right? I will be contradicting only in one case. When you have solved the problems correctly, but I don't give you the tab. That is the only case when I will be false. Is that right? Yes or no? Huh? So that is the sense we will be taking. The other sense will come when you say it is if and only if. Not one side, but both the sides. Right? So that is the only case when you say that. When you say that I am wrong if one of them is having different values, right? This becomes true, the other becomes false, or this becomes false, the other becomes true, right? That happens in if and only if. But if it is one sided, then it is false only when P is true and Q is false, right? In all the other cases it is true. Is that clear? So which means we can say that this becomes true when P is false or when Q is true. That covers all the 3 cases. Is that okay? Does that cover all the 3 cases? Check it. Huh? Does that cover all the 3 cases? If P is true, Q is false, that case only this becomes false. I am only writing the true cases, right? So there are 3 cases for the true. I say that this covers all the 3 cases. Huh? So in that case I will say Q is true, that is why it is true. Forget about P. Okay? So when you say P is false, what about Q? I am not thinking about it at all, right? Whether it is true or false, does not matter. My statement is true, because you have not answered correctly all the questions, so I do not bother about it. Is that okay? Clear? So this is very crucial thing that happens in mathematics, that you have to understand this if then first. This is very contradictory thing sometimes to our natural language use. Have you read about Buddha in history? Huh? Yes? So one of the basic rules, he told that if you have desire, you will get pain, right? So not to get pain, have no desire. How does it follow from it? It is really if and only if statement, right? That is why it follows, otherwise it does not. Okay? So you have to understand in which context how this if then has been uttered. Then you can say whether it is mathematical if then or it is our natural language if and only if statement. First you have to understand it, see the sense in it, then go for it. Fine? But in mathematics invariably this is the sense of if then. That is what we will be using. Fine? Now suppose there is a sentence which ends with something something is happening, then finally one sentence comes. If this happens, then this happens. Now, we require a proof whether this is correct or wrong. How do we prove it? How do we prove it? Abstractly I am speaking, I am not giving any example. We need like that. Suppose you have some sentences, some conditions given. S1 is one condition, S2 is one condition, S5 is one condition. Right? There are 5 conditions given. Then you utter another sentence. Over and above that, if P, then Q. Right? So, how do you prove it? You assume all of them S1 to S5. That is the case that is given to us. Then, where to start with? If P, then Q. How do you start with? Again you assume P, right? One more thing. Out of all those 5 sentences, they are assumed. Over and above that, you take, suppose P is also true. Then finally, what you will derive? Q is true, right? Because that is what you wanted to show. But if P is false, you are not assuming P is false, right? Why you are not assuming P is false? Because whenever P is false, if P then Q is true. So, there is nothing to prove, right? That is what we see here. Automatically, when P is false, if P then Q is true. So, why should I go for it? It is already known, right? So, you start with suppose that P is true. Then finally, you end with Q is true. So, automatically, if P then Q becomes true. Is that right? What other way you can prove it? What other way you can prove it? Yes? Loudly? Someone told there. Loudly? What other way? Assume conditions to be wrong. Then automatically if P then Q is true. Not conditions to be false. If conditions are false, then automatically everything follows. No? If P then Q is true. Which one is false you are assuming? Yes? Any other way you can prove? Right? What he says that, suppose P is true, I have assumed. Now where I should end? Q is true, right? Is that okay? I should end with Q is true. Now suppose instead of ending with Q is true, I assume Q is false. Then what happens? That means I will become false. If P then Q will become false, right? So that means I am assuming, suppose whatever I have told is false, right? If P then Q is false, then what happens? There should be something wrong, right? That is what, that is the feeling, because it has to follow from it. If you assume S1 to S5, if P then Q should follow, right? But you are telling suppose it is false, means it does not follow from them, then there will be something wrong somewhere, right? So what will happen? You will say that there will be a contradiction. So to prove this, what you do? Assume that the sentence given is false, then you show that there is a contradiction. How do you get a contradiction? I don't know how do you get, it depends on the particular places, right? In different types of arguments, different types of thought may be required to get a contradiction, fine. But the contradiction will be in a form like something is true and also the same thing is false. Both the things you will be able to deduce from it. Is that okay? Yeah? So that means if I want to prove some sentence, we will say let us go by proof by contradiction. How do we prove? We assume that false, then find that some sentence is true, simultaneously that sentence is also false. Both the things will be coming from it. Is that okay? Then it should be wrong, there should be something wrong. But given all the conditions true, they cannot be false. The other one is false, I have assumed. That is wrong. So it has to be true. Is that okay? So it is a second level argument. Assume that it is false, therefore something is wrong, therefore it cannot be false. Right? That is what we are doing in proof by contradiction. Fine? So there is another kind of proof. to prove this if P then Q, I can do some other way. I will not assume anything about P, right? I will assume the falsity of Q. Suppose Q is false, then what do you expect? I have S1 to S5, then another sentence, if P then Q, right? Now I assume S1 to S5, I assume Q is false, then what do you expect? P should be false, huh? Right? Yeah? If P is true, then this sentence becomes wrong, right? So it should follow that P must be false. So really what you are proving then? If Q is false, then P is false. That is what you are proving. Yeah? Is it okay or not? So here instead of this, what you are proving? If Q is false, then P is false. This is what you are proving. Okay? So in fact this sentence and the other one, if P then Q, they are equivalent. If you prove one of them, the other is done. If you prove second one, the first one is also done. They are called the contrapositions of each other. Huh? So this proof is called proof by contraposition. Contraposition, their positions are changing and the negation is coming up, right? Is that okay? So any one of these three methods usually we use. Okay? But there is another tricky thing that we want to discuss now. Suppose I want to prove that P. Okay? Now what I do, I assume not P, derive P. Now question is, have I proved P? Huh? This is a tricky thing. What happens is, I want to prove what? P, some sentence P, right? What I do? I assume not P. Then do some mathematical gymnastics, right? Finally, you derive P. Okay? Now, do you say that you have proved P? I am only giving this much. Is it enough to do this? Think a bit and tell me. I have only done this much. Now I am claiming I have completed the proof. Not P was not given to me, right? I have assumed it myself. Now I am claiming I have completed the proof. Am I wrong or correct? Wrong, huh? Yes? We will see a proof today basing on this. So can't say? Okay, start from the beginning. Huh? Nothing is given to me. I have to prove P. No conditions, nothing is given. I have to prove P. Then how do I start? I don't know how to start. Right? So what I do, I will do a trick. Either P is true or not P is true. Right? One of them has to be true. Right? If P is true, then P is true. Right? If not P is true, I will prove that P is true. So in both the cases, P is true. Right? Is that okay? So it's enough just to show the right hand side. I forgot the left hand side. That is always true vacuously. Possible? Why not? It is quite possible. Correct. Now if not P is true, from that I derive that P is true. So which one I am contradicting? Not P I am contradicting, right? So not P is false. That's why not P is false. So P is true. Do you see the reason? Huh? See what you are telling, if not P is true, then how can P be true? But I have derived it. Right? So which says that both P and not P are true in that case, but both cannot be true. So there is a contradiction. So the contradiction says whatever I have assumed is wrong. So not P is wrong. Therefore P is true. Right? Yes. Could be true. Suppose not P is true. Then P is false. But I have derived P. So P is true. So it cannot be true. Not P cannot be true, right? Because it leads to a contradiction. What is the contradiction? P is both true and P is false. Right? Is it clear? So this is a very powerful method sometimes. It is really proved by contradiction, nothing more. But it leaves that case which is uninteresting, which says that if P then P. Right? So that case, uninteresting case, we are just forgetting it. We are assuming with not P and deriving P. Fine? So interest are, instead of telling that from not P derive a contradiction, from not P I derive P, thereby I get a contradiction P and not P. Right? That is the beauty of it. Is that clear? So sometimes this abstraction is easier to understand than giving an example. That's why I went with PQ. Okay? If you are confident, then we will proceed. Fine. Okay, let's see whether you have understood this and or also. Suppose A is a set. Okay, is this problem clear? I start with a set A. Fine. A is having what? Some natural numbers, not necessarily all natural numbers. It is some set of natural numbers. Right? Then what I do? I define my another set B. How is B looking like? I pick up those elements satisfying this. X is an odd number and also X is a square. Okay. So how are you going to construct this given one A? Suppose A is given from 1 to 100. Right? Now, how are you going to construct this B? See, first thing is you have to choose elements from A. So let me choose from 1 up to 100. Let me see whether each one of them satisfies my condition or not. I start with 1. So 1 is an odd number. 1 is also a square, so I keep 1. Then I go to jump. I go to 2. Right? See what happens for 2. 2 is an odd number? No. 2 is a square? I don't have to check now, right? Because both the conditions have to be satisfied. One of them is not satisfied, then gone. It cannot be satisfied. Both cannot be satisfied. So I leave like that up to 8. Then I take 9. Okay? Is that right? 9 is odd? 9 is a square? Yes. Then next. Because it is odd, so it should be odd square. So I have to check only 1 square, 3 square, 5 square, 7 square, 9 square. Then? That's all. I can list my element B. Fine? Is that okay? Now instead of and, I put it or. Then what should we do? Okay. So can I write like this? Can I write like this? It is not that, it is something else. It is not that. But is it that or not? If you do this process, will you get the same B or something else? Sometimes you will get something, you will get something else. Now think about it. See, if I do this, whether I get the same B or a different B. Huh? Okay, let us see. Now, what about this B? Is 1 there? I have 1 to 100. Is 1 there? Yes? Is 2 there? 2 is not odd. 2 is not a square, so it can't be there. Neither of the conditions is satisfied. Right? So 2 is not there. Is 3 there? So collect all odd numbers first time. So how do I do? The first line what I wrote, collect all odd numbers. I will be starting with this set 1, 3, 99. What I am telling then? And all those which are squares, right? So suppose I do that, I will take 1, it is there. I have to take 4. Odd squares I need not take because all odds are there, right? So I have to take 4. Next, 16 I have to take. Next, 36. 36. Yeah. So are they not same? Are they not same? So this is what I have got by following my rule. Collect all the odd numbers and also all those which are squares. This is how I get. Now look at the definition of B. Tell me one element which is in B but not in that set if A is equal to 1 to 100. Which element is in B but not in that set? Hundred is there. 2 is not in B. 1 is there. I don't have 0 in A either. In A I have only 1 to 100. Which one? A equal to 1 to 100. I have not taken every. It is an example. I take A from 1 to 100. Then we are working with that example. It's correct, right? So this OR has become AND, you see. It was written as OR inside, outside it has become AND. In this manner, if I describe, it becomes AND. So be careful about this, OR, AND, if then, and these things. You have to see the sense always. Right? So what is happening here? Why that OR is becoming AND here when you write it outside? Because when you go to the definition of the set, you have to verify each element. That's why I told you start with 1, don't jump to 9. Take 2 also, see what happens. That's why I told you to do. So you have to find out which element in A satisfies both the conditions or one of the conditions. According as it is AND or OR. It is an OR. So at least one of them should be satisfied. I am happy to keep it in my B. Right? So that means all those which satisfy first condition will be in my B. Right? What extra can be in B? All those which satisfy the second condition. Therefore, it is really AND. Collect all those which are in satisfying first condition and collect all those which are satisfying second condition. Now I am collecting. But when I see element wise, the condition has to be told as OR, not as AND. If I say AND, it becomes different. You have seen already. Right? Is that okay? So they are the same sets. There is no difference. Is that okay? Now let us go to set difference. You know that already. Suppose I have a set A and I have another set B. Then you know what is A minus B? Yeah? How do you write it? Like this. This is equal to set of all x in A which are not in B, right? Like this. You know this or not? Which are in A but not in B. Okay? So suppose both of them are from a bigger set. How do you write it? Both A and B are from a bigger set. Say A, B as subsets of some C. Now I want to write A minus B as element wise from C. How do I write? How do I write it? Yeah? Not A intersection. I want A minus B. A minus? But how do I write like this? That is what I want. I want to write like this. It's easy. You write like this. Easy, no? They are from a bigger set. So what happens? I look at all the elements of C and then choose. Which one? I will choose that one which is first in A. Next, it should be outside B, right? That is how I am choosing one by one. Is that right? So you can also write in terms of AND using the same thing. Yes or no? Yeah? That is easy to write. But what happens with the sets? We have to really do and see that they are acting, they are not static elements, they are not dead elements, they are life. How do you see life? Life will come by throwing them out, take it from one place, throw it to another place and so on. Okay? So what is that? You put the sets into action. By which do you put the sets into action? Yes? Usual things, no? Suppose I tell you that you take one number, square it. So now what happens? Something is happening, right? Some action is happening, square it. So now you are throwing 1 to 1, 2 to 4, 3 to 9 and continue like that. What is that you are doing? You are defining something there. Functions, you are defining functions. It is a square function. Okay? So functions are really giving life to these sets. So see how they are moving together. That's how we will be looking. Fine? So you know functions also, right? Or not? You know functions? So how do you say whether this is a function or not? This is how you write functions, right? So what does it do? What does it do? You take any element from A, then it says that something is, it is moving to some element in B, right? It is pointing towards some element of B. Okay? That is the assignment. It assigns to something. But it does that for every element of A. If some element is left out, then you don't say that it is a function on A. Right? Okay? Is that fine? And the mirror is straight here. It is not a broken mirror. If you take one element from A, you will not get two images here. Fine? You will get a single image. Fine? But two persons can have the same image. So that way it is curved. It is not very straight that way. Yes or no? Suppose you take the set of all real numbers. Now you give the square function, f of x equal to x square, fine. Then what happens? If you pick up 1, it will have one image 1, pick up 5, it has one image 25, pick up one image, one number root 2, it has one image 2, right? That is how it goes. But there can be 2 whose image is same, right? 1 minus 1, they have the same image as 1. So many other things also like that. Is that okay? So it is a straight image in that sense, but also curved in the other sense. There can be many things which will be giving you one element. Okay, there is a possibility. So you take out them. What do you say? You already know these things. Tell me. You say function is 1 to 1. When? When the second thing does not happen, right? Each one has a particular image, right? It is not that one. Each one has already a particular image because of f. But what happens there in 1 to 1? Two distinct elements cannot have the same image, right? Okay? So that means if x is not equal to y, then f of x is not equal to f of y. They cannot be equal. If x is not equal to y, then f x and f of y cannot be equal, right? They have to be different. Is that okay? That happens in 1 to 1. Now, what is the contraposition of this? Right, write that sentence. Say f is 1 to 1 if first sentence you write. F is 1 to 1 if whenever x is not equal to y, f of x is not equal to f of y, right? So this happens for which x y? This happens for which x y? All x y in A. All x y in A. F is a function from A to B. So this happens for all x y in B, right? If it happens for some of them, then do you say the function 1 to 1? So we have now two words. Be careful about these two words. What are they? Something might happen for some of the elements, or it can happen for all of the elements, right? When you say some of the elements, it means at least one, right? If there are two elements involved, you say at least for one pair, okay? So that is a twist of language. Or you say it can happen for all of them. So these two words very important for us. Is it happening for some of them, or it's happening for all of them? So you say that f is 1 to 1 when this condition is true for all x y in A, fine. For each x, for each y in A, whenever they are distinct, their images must be distinct. Now what is the contraposition of this? We want contraposition of if then, not for all. We want contraposition of that if then only inside. So what is that if then sentence there? If x is not equal to y, then so what is contraposition of that? Top, somebody can say. What is contraposition of that sentence? It is not a sentence really. Inside that, if x is not equal to y, then f x is not equal to f of y. What is contraposition? Loud. Right. So that is the contraposition, right? See, if p then q, its contraposition. If not q, then not p, right? So here it will be if x, f of x equal to f of y, then x equal to y. So you don't know which one will be helpful when, right? We should be prepared to keep both of the tools ready. In some cases, that way it will be easier to prove. In the other case, this will be easier to prove, right? So, you must know both the things at a time. Fine. So, that is how we define the 1 function. Okay. Now, suppose I take a minus b like this. So, now this a minus b, all these a and b are subsets of C. Okay. Now, I take a function f from C to some d. What I have done? I have a big set C. I have subsets a and b. Okay. Then I am considering a function from C to d. Okay. Now, I am giving that f is 1 to 1. Okay. What can you say about this f of a minus b, and on the other side f of a minus f of b? First thing is same. Anyway, whatever it is. Otherwise, why should he ask us? Okay. Can you give me one example of a function which may not be 1 to 1 and these are different? So, try with a many one function, right? Say like your square function and the real numbers to real numbers. Okay? Now, can you construct this a and b so that a minus b, that image, square image, right, will not be equal to the other side? By the way, what is f of a? What is f of a? All those points which are images of elements in A, right. So, let us write like this. Okay. You know what is f of x for a particular element x, then collect all those elements where this small x varies over this capital X subset. So, that is the whole image. When you say your image on the mirror, what do you see? Do you take only your image of the nose? Nose is there, ear is there, all image, right? That is your f of x from a subset we are taking. Okay? So, that is how it looks. Now, tell, can you get one example where they are not equal for the square function R to R? Can you construct one set A, one set B, so that A minus B will not go to f of A minus f of B? Yeah? Can you get or not? No? Very bad. For the square function, try something. Try now itself. Also take minus. Don't leave minus because many one has to be used, right? So take also minus elements. Take also minus elements in A. So, suppose you take A as 2 element set 1 minus 1, B as the singleton 1, what do you get? F is the square function from real numbers to real numbers. A is the set containing 2 elements 1 and minus 1, B is the set containing 1. Now, compute, see what happens. F of A equal to f of B, that is the singleton 1, is that okay? Because 1 goes to 1, minus 1 goes to 1, so f of A equal to 1 only, singleton 1, right. Now, f of B equal to singleton 1, but A minus B is what? So, f of A minus B is singleton 1, what is happening? They are not equal, right? Yeah? They are not equal. It may not happen. But if it is 1 to 1, this will happen. For many 1 only there is problem. For 1 to 1, it will be easier to see. Right? Then you see what happens. Suppose you consider only the positive reals. Right? Positive reals to positive reals. Now the same function x square is 1 to 1. You will never get such an example. Right? So we have proved. We have proved this. It is equal when f is 1 to 1. Yes? You are studying logic. Yes or no? Tell. There is either yes or no. Huh? We haven't proved it. We have seen only an example, that's all. Okay? Then you can prove it. Take it as an exercise. If f is 1 to 1, then both the sides will be equal. That can be done. Right? Okay, let us look at these maps. They tell us many things. See, there is one tribe in Africa who do not know the numbers, like we know the numbers, right? So one person was on a safari in that place, then he happened to find a tribe person. He asked the tribe person, how many children you have? He said many, right? So he was confused, what does it mean, many? He is not telling me anything, how many children you have? Then after some time he told, okay, I can ask him like this, how many children you have? Then he said no. Then he said no, no, yes, right? So he has really 4 children. That's how he found out, fine. But in the beginning he told many. Now then this person was confused. He told, how many cattle you are having? In your cattle, herd of cattle, how many buffaloes are there? So he says many, right? Because he doesn't know how many number, what number it is. Then this fellow got confused. In the evening when they come back home, how do you take care whether everybody has come or not? You have so many. So now imagine and tell me, what would he have done? How does he take care? It's more than that, it's big herd. He can't keep like this in fingers. What should he do? Lines somewhere. See what he actually does, this person has found out that there is something hanging here, right, on that tribe's person. So he asked him, what is that hanging on this place? He told, it is a small bag and there are pebbles in it. What do you do with pebbles? I use it for taking care of my cattle, right? So how does he take care of his cattle? He doesn't know number. He doesn't know the number. So when the cattle come back in the evening, what he does? He takes this, then one cattle comes, he throws one out, another cattle comes, throws it out, right? So now he sees that everything is over and this is also over. Now he is happy, right? He doesn't know the number, how many are there. He just knows it is many, but he is able to count, right? Okay? So you can compare number of elements in 2 sets without knowing their number. Yes? You can do this or not? How do you do? Suppose A and B having the same number of elements. So how do we define that they are having the same number of elements? There should be a 1 to 1, something else, on 2 also, because nothing is remaining in his bag. He is defining 1 1 map, it is also on 2, right? So that is called a bijection. If there is a bijection between 2 sets, you say that they are having the same number of elements. Is that right? Now suppose it is not a bijection. Suppose A is having less number of elements than B. Then what do you expect? A is having less number of elements than B. B is having more, possibly. Which cannot be 1, 1, 1, 2? From A to B or from B to A? Let us take A to B. Okay. Now, if I take from A to B, what I will get? I will get a 1, 1 map, but it will never be on 2. So, if it is less, then there exists one 1, 1 map, but no map is on 2. Not only that, no map is on 2. Take care here. You say that A has less number of elements than B if there is a 1, 1 map from A to B, but no map from A to B is on 2. Is that clear? Fine? Agreed with this? Now, when you say A has possibly less elements than B, means less than or equal to. Number of elements in A is less than or equal to number of elements in B. When do you say? Yes? Both the cases you have to take. So, either way we can say there is a 1, 1 map from A to B, over. Once 1, 1 is there, after this is over, the range may be equal to B, may not be equal to B, right? A 1, 1 map is enough. Or you can say there is a bijection between A and a subset of B, right? That range of A, which is subset. So, you can also tell in terms of bijection. Fine? Agreed? Now, how many elements are there in the set of natural numbers? 100? How many elements are there in the set of natural numbers? Infinity. 100. It is not 100, right? Because I have 1 to 101. So, I cannot have a 1, 1 map from 1 to 100 to 1 to 101. How do I count? I say 1, 2, 3. So, I am having a 1, 1 map from 1 to 100 to that set. Once I have a 1, 1 map, I say it is having 100 number of elements, right? So, 100 to 101, there cannot be bijection. Is that okay? So, it does not have 100 elements, more than that. Billion? More than that. 1 billion plus 1, right? So, no finite number. That is why you call it is an infinite set. There are infinite number of elements in it. Okay? Infinite number of elements. But then there is a problem. I can have a bijection to a proper subset of itself. Yes or no? If it is a finite set you told, 101, I say up to 100, I cannot have a bijection. But if I take natural numbers, I can have a bijection to a proper subset of itself. Can I have? Example? F of n equal to 2n. You have to give the map, right? So, f of n equal to 2n is a bijection 1, 1 onto the even numbers, right? But even numbers is a proper subset of that, right? So, for finite sets that does not happen, but infinite sets that happens, right? You can have a bijection to a proper subset of itself. Yes or no? Yeah? Why can't it happen to finite sets? You see, suppose A is a set, B is a proper subset of itself. Where is the bijection? Where is the bijection? Tell me the bijection. Where is it? So, after 50, what are those things? Where goes 51? Understood? Okay. So, these infinite sets, because they are having bijections between those sets and the proper subsets of themselves, so there is the problem, right? It creates a problem. See, for example, you have another nice thing. Sorry, I should switch off this. Okay. So now, what is the problem? The problem is this. Suppose you have natural numbers. Okay. Now, there is another set which is like natural numbers. For example, negative of those things, right? Say 1, 2, then I have -1, -2, -3, -4 and so on. Everything is there, right? Now, what I can do? I can take the union of those two things and then define a bijection. This is creating problem. Huh? Okay. So, what should I do? I am taking the union of those two. Now, I claim that there is also a bijection between that and the natural numbers. You have seen a proper subset. I am not taking proper subset, I am taking a bigger set, right? And still I am telling there is a bijection between that bigger set and these natural numbers. Can you do that? Yeah? Yes or no? Huh? If I take only 5 elements extra, -1 to -5, then I have -1 to -5, then natural numbers. Now, can you have a bijection between this set and the natural numbers? Now comes imagination. Imagine we have a big hotel where the room numbers are 1, 2, 3, 4 and so on. It is a big hotel, not like our usual hotel of finite number of rooms. It is a set of natural numbers, right? Now, all rooms are full. 5 people came. How do I give them rooms? How do I give them rooms? I will shift first room number who we are staying, go to room number 6. 2 will go to room number 7. N will go to room number n plus 6. Right? So now my 5 rooms are vacant. So I will put -1, -2, -3, -5. Can be done? Yeah? Is that okay? Now it is not any finite number people are coming, but infinite number people are coming, just like n. Now how do I adjust? Everyone to even number, right? It is twice. Say n will go to 2n. So 1 will go to 2, 2 will go to 4, 3 will go to 6, 4 will go to 8. So all odd numbers are vacant now, right? So I will put all these n into that odd number. We can accommodate. Is that okay? Now comes a better imagination. Suppose what I do, you have to imagine it really. Imagine that all of us are in hell, not here. Okay? And I am the devil. Okay? So now all of you are my victims. Fine, all of you are my victims. I put a condition. I write a number and keep it with me. Every day you come and guess that number. Once you tell me what number it is, you will be out. Right? You will be out from the hell. Okay? Now, what strategy you will follow? I will write a natural number. So, what strategy you will follow? You go on telling, first day you say 1, second day you will say 2, third day you will say 3. Someday I will hit it. Right? So, that day you will be out instead of telling randomly. Is that okay? Now what I do, I don't do that. It is very easy. So I don't want to leave you. You are nice people. I want to keep you in hell. So what I do, I say that I will not write one number, I will write a pair of